Hello and welcome to this video where we'll discuss a little more on the common source amplifier. So in this video, I'll discuss some methods, intuitive methods to evaluate common source circuits, and then we'll look at what the impact of the source resistance would be on the properties of the common source amplifier. So many a times when you're analyzing circuits, right, you need to familiarize with the small signal models. Typically what we have done so far is when we look at a circuit, we replace the transistor with a small signal model and then we go ahead with the analysis. But then what is the small signal model? It's nothing but the linearization of a nonlinear characteristics of the transistor around the bias point. So sometimes to build that intuitive understanding, it's sometimes effective to think about how the MOSFET looks like in small signal directly by looking at it either through the gate terminal, the source, or the drain terminals. So what we'll understand in this section is how do we think about the MOSFET in small signal when we're looking into any of a particular terminal pair of the MOSFET. So let's first look at the simplest case. When you consider an NMOSFET here, again this is a 3-terminal NMOSFET, and you're looking into the gate terminal. That is, you're seeing how does this transistor look like in small signal if I look in the gate terminal. What I mean in other words is that suppose I apply a voltage across the gate and source terminal, what is the current or small signal current this particular transistor will pull into the gate terminal. Right? Now obviously we know that in small signal at mid band, the MOSFET small signal model looks something like this. The gate to source is open and the voltage across the gate to source is converted to a current between the drain and source. So if I look into the gate is basically an open circuit, and so we expect the current to be zero. So if I'm looking into the gate of a MOSFET, what that means is there is no current that's flowing through the gate terminal. In other words, the input resistance is infinite. So in other words, it means that if I'm looking at the gate terminal of the MOSFET, I'm looking into an open circuit. So now let's flip it and try and see what happens if I look into the drain terminal of the MOSFET. So again, this is an MOSFET biased in saturation. And we'll see what happens if I look into the drain. In other words, I've biased it such that the transistor is in saturation, which means there's a certain gate voltage, there is a certain drain to source voltage, and then suppose I increase the drain voltage, what happens to the current, small signal current that flows between the drain and source? So again here, if you think about it from a small signal point of view, the gate is biased at a DC voltage, so in small signal the gate goes to ground. And so what we see is that in that case, in small signal, the MOSFET, if I look into the drain, looks like a resistor whose resistance is nothing but R0, right? And so when I apply a voltage only at the drain, the MOSFET, if I look at it into the drain terminal of the MOSFET, it's going to look like a resistor of resistance R0. Now remember, this resistance R0 is the small signal resistance, and it's going to be determined by the bias conditions on the MOSFET. Now let's look at the final case when we're looking at the source of the MOSFET. And again, remember, this transistor is biased in saturation. So when the source voltage changes, not only does the drain to source voltage change, the gate to source voltage also changes. Right? So when the source voltage changes, you see that it impacts the current through the drain to source because of a change in GS and because of a change in DS. Right? So if you look at what happens to the small signal model, basically I have a small signal model here. The gate is grounded because it's a DC voltage. The drain is also grounded. And the source I've applied a small signal. So I want to measure what is the current that is being drawn from the source terminal in this case, right? And so if I apply a Vin at the source, VGS is automatically minus Vin, which means that there is a current that flows into the source. This GM VGS turns upwards. So we have a GM times Vin flowing upwards and then an R0. So in other words, I can write my IN as Vn upon 1 by Gm plus Vn upon R0. In other words, the input resistance looks like a parallel combination of R naught and 1 by Gm. Right? And typically, in most cases, R naught is a large number, 1 by Gm is a small number, so sometimes we approximate it as 1 by Gm. So, what you see here is that in DC, the MOSFET drain and source are identical. But once you look at the MOSFET in an AC signal, it is very important to know what the source of the transistor is. Because if I look into the drain of the transistor, I'm going to see a high resistance. If I look into the source of the transistor, on the other hand, I'm going to see a small resistance in small signal. So this is something you need to keep in mind, that when you're analyzing circuits in small signal, the drain and source are not interchangeable. The drain and source are interchangeable when you think about it at the large signal modeling of the transistor. Now let's look at a simple method of biasing a common source amplifier using just one power supply, which is VDD. So a simple way would be, so remember this is a common source amplifier, and so if I think about it, I need to ensure that M1 is in saturation, which means I need to apply gate voltage such that, and ensure a drain voltage such that this transistor exists such that VDS is greater than VGS minus VT. So to apply the DC bias, I can generate the DC bias from VDD using a resistive bridge, right? And so if I think about a small signal gain of the circuit, the small signal gain is going to be given by GM1 times R1 parallel RD, because RD is the load on this transistor, right? So if I think about it, therefore, I need to select the right combination of RG1 and RG2 so as to target for a given GM1, right? And if I look at what that gate voltage would be, very simply given up by RG2 upon RG2 plus RG1 times VDD. Now, as we looked at in the first video, resistor-based biasing is non-optimal, primarily because resistors by themselves are large area circuit components and they are hugely temperature dependent, so the circuit tends to drift a lot at usage. Now let's look at a different configuration of the common source amplifier, and let's try and apply the intuitive method to extract the small signal gain. So here if you look at this circuit, you identify it's a common source amplifier because you see that the signal is being applied between the gate and source of a transistor, and the output is being collected between the drain and source of the transistor. And hence this is a common source amplifier. What you also see is that M1 is the transistor that is providing the transconductance. That is, M1 is the transistor that is converting this input voltage to a small signal current. And how are you generating this V0? This V0 is being generated because this current that you're generating is going to basically flow through the resistor self-resistance of M1 and the load that is being provided by this transistor M2. Right? So to identify what the load provided by M2 is, I basically need to estimate what the small signal resistance of this component is. Now what is M2? M2 is a PMOS, right? Whose gate is held at some bias voltage, its source is at VDD, and I'm looking into the drain of M2. So because I'm looking into the drain of M2, the resistance that it's going to provide to the circuit is going to be RO2, right? So therefore, if I think about the gain of the circuit, it's going to be minus GM1 because M1 is doing the transconductance times the net load, which is R1 parallel RL, and in this case RL is RO2. So the small signal gain of the circuit is going to be given by minus GM1 into R01 parallel RO2. So what we are employing in the circuit is we are identifying what the transconducting element is, and that provides the first part of the small signal gain. And then we identify what the load is, the small signal load is, and so GM times that load gives you the small signal gain of the circuit. Let's look at another configuration here. Again here, M1 is the transconducting transistor. Why do I say that? M1 is connected in a common source configuration where the input is applied between the gate and source. The output is pulled between the drain and source. So again here now if I want to estimate the small signal gain, it's going to be GM1 times the net resistance at the output. So if I look at the output resistance of this circuit, I'm going to have the resistance of M1, which is R01, in parallel with the resistance provided by M2. Now we need to identify what the resistance is of M2. Now here, in this case, M2 is an NMOS, right? Where the NMOS with the gate and drain tied. So this configuration is a NMOS that's going to be always in saturation. And you're essentially looking into the source of the NMOS transistor, right? So the small signal resistance provided by M2 is going to be 1 by GM2 parallel RO2. So that's going to be the resistance provided by M2. Resistance provided by M1 is going to be RO1. M1 is also the transconducting transistor, and so therefore my voltage gain, small signal voltage gain, is going to be given by minus GM1 times RO1 parallel this resistance, which is 1 by GM2 parallel RO2. And so if you now think of a limiting case where RO1 and RO2 are very large, right? In that case, the gain can be simplified as the ratio of the transconductances, or GM1 by GM2. Let's look at this configuration. Now here you see that this, for most of you have done digital design, this looks like the CMOS inverter. You have a PMOS and the NMOS whose gates are shorted. The input is given here and you're collecting the output at the common drain. Now this is not the digital CMOS inverter because you see here that you're looking at this small signal analysis, and so you're looking at it in the very small region where both M1 and M2 are in saturation. So how do I find the small signal gain of the circuit? So first thing you need to identify what kind of an amplifier this is. Now here you see that this small signal is being provided to both the transistors M1 and M2. So first of all, we expect that the gain is not going to be M1 alone. It's going to be dependent on both GM1 and GM2. Now here we apply the principle of superposition because now we have a circuit where a signal is being given to two transistors. So I'll break this circuit into two subcircuits, one in which the signal is given to M1 and the other input to M2 is grounded. And I think of the second subcircuit as one where the signal is given to M2 and the input to M1 is grounded, right? And so now these two individual circuits are easy to analyze because I have input going into only one transistor. And so I can estimate the voltage gain of this circuit, estimate the voltage gain of this circuit, and the sum of these two is going to be the voltage gain of the overall circuit. So now let's estimate the gains of the two circuits. So first thing is, let's identify which is the transconducting transistor in each circuit and which is the load. So in the first circuit, the input is given to M1. So M1 is the transconducting transistor and M2 provides the load for this circuit. And so if you think about the voltage gain, we've looked at this before, it's going to be minus GM1 into RO1 provided by M1. And you're looking into the drain of M2, so it's going to provide a load of RO2. So hence my gain is given by minus GM1 into R1 parallel RO2. If you look at this circuit now, the second circuit, here my input is applied to M2. So M2 is my transconducting transistor. So this is a PMOS common source amplifier. M1 is the NMOS that is providing a load to M2. And the load provided by N1 is found out by looking into the drain of M1, which is nothing but R1. And so here the gain is going to be given by minus GM2 into RO2 parallel RO1, right? And so therefore the total gain of the circuit is just the sum of the two gains. And you see that it's equal to GM1 plus GM2 into RO1 parallel RO2. And this is kind of expected here because you see that because the input is given to both the transistors in the circuit, both the transistors are going to contribute to a transconductance. And so expect the gain of the circuit to be larger than what would have been suppose one of the transistors were only given the small signal input. Now let's look at this example here and identify what kind of a circuit is this. So here again I want to find what this voltage gain is between V0 and Vin. So first thing is you identify the mode of the circuit. So you see here that M1 is the PMOS transistor The small signal is applied at the gate of this PMOS transistor between the gate and source, and I'm pulling the output from the drain of M1. So this is a common source amplifier where M1 is transconducting the signal and M2 is providing the load for the circuit, right? So the way I would do it is that the small signal gain is going to be of the format minus GM1 into the resistance of M1 and the resistance of this circuit connected here. So let's look at the load. So to estimate the load, I'm looking into the PMOS source, right? M2 is a PMOS whose drain and gate are tied. And so therefore here I have the load is going to be represented by looking into the source of M2, which is 1 by GM2 parallel RO2. And so therefore my gain is going to be minus GM1 into RO1 parallel RO2 parallel 1 by GM2. So that's going to be the gain of this circuit. Now let's look at what happens. Suppose there is a finite resistance that is connected to the source terminal. In other words, my common source amplifier looks something like this. Previously we made the case where RD was the load, there was no RS. So now let's assume there is an RS connected in the circuit. Now this can happen because of the pin resistance of the source or because you've intentionally connected a resistance in the source. Now again, like always, to make sure that the gain is linear, you want M1 to be in saturation. And to ensure M1 is in saturation, we first calculate VGS. So the VGS of this transistor is no longer the gate bias VG because the source of M1 is not at ground anymore. The source at M1 of M1 is at some IDRS above ground, right? Because there is a constant bias current of ID that flows from the drain to source of the transistor. So therefore VGS of M1 is given by VG minus IDRD. The VDS of this transistor is given by VDD minus IDRD minus IDRS. So it's VDD minus ID into RD plus RS. And to keep M1 in saturation, you want VDS to be greater than VG minus VT, which gives you the relationship that VDD minus IDRD should be greater than VOV or VG minus VT. Now for hand calculations again, typically as you've seen before, hand calculations help us give a starting point for simulations because they are very simple. In reality, transistor models do not follow square law, but square law gives you a starting point to run your virtuoso simulations. So for hand calculations, we generally tend to neglect channel modulation for DC currents, and we assume that the current is just given by half Kn prime W by L, the size of M1, into Vg minus IDRS, this is VGS, minus Vt the whole squared. Now let's estimate the small signal gain of the circuit. So the first things, let's keep it simple. Let's assume lambda is equal to 0. So there is no channel length modulation in this transistor. So therefore, if I now replace M1 with its small signal model is going to just look like VGS and the GMVGS connected across the drain and source. The input is applied to the gate of the transistor. RS is connected to the source of the transistor, and RD is connected to the drain and connected to signal ground. Right? And now here in this circuit, I need to estimate V0 upon Vin. Right? So if I apply KVL in the input loop, if you see what the current flowing in RS is given by GM1 times VGS times RS. So if you look at the input loop, GM VGS is the current that's going to flow in RS and it's going to flow back in RD. So I can write my Vin as VGS plus the voltage drop in RS, which is VGS plus GM1 VGS RS, or 1 plus GM1 RS into VGS. V0 on the other hand is going to be minus GM1 into VGS into RD because the current is flowing upwards. So I express Vin and Vout in terms of VGS. And so therefore, I can now write my small signal gain AV as V0 by Vin, which is minus GM1RD divided by 1 plus GM1RS. And so basically what's happening here is addition of the source resistance reduces the small signal gain of the circuit. Now, if I look at the input and output resistances, the input resistance, again, because the input signal is connected to the gate and the gate is an open circuit, the input resistance is infinite. The output resistance, when Vin is 0, this current source disappears, so all we're left with is RD. So the output resistance is given by RD. Now let's see what happens if I include R0 in the analysis. So if I now consider there is a finite lambda in M1, so this is what the small signal circuit looks like. In addition to GMVGS, I have an R0 that is connected between the drain and source. So let's now look at how the currents flow in the circuit. So suppose I assume that a current V0 upon RD flows in RD. That same current is going to flow upwards in RS. And then the current flowing in R0 is going to be GMVGS plus V0 by RD. Right? So once I've established this, then it becomes easy to write the equations. So first thing is, if I apply KVL in the input loop, Vin is given by VGS plus the voltage drop across RS, which is minus V0 into RS by RD. Similarly, so therefore my VGS can be expressed in terms of Vin and V0. Same thing, I can write the output loop resistance voltage as V0 is also given by the voltage drop across R0 plus the voltage drop across RS. So therefore I can write it as V0 as minus V0 into RS plus R by RD minus R0 into GMVGS plus V0 by RD, which is the current flowing in the R0 transistor. And so I can collect all like terms and express VGS in terms of Vin and V0. And then what I get is the expression that the voltage gain V0 upon Vin is given by minus GMRO divided by 1 plus RS plus RO by RD plus GMRO RS by RD. And so this is the voltage gain, which is minus GMRO RD divided by this expression here. So you see that when RO is considered or taken into consideration, the gain is not very simple, but you can establish what the gain is. Now, as R0 tends to infinity, you'll see that this gain drops to GMRD upon 1 plus GMRS. Now again, if you look at the input resistance of the circuit, the input resistance continues to remain infinity because the input is applied to the gate and the gate is an open circuit. Now let's see what happens to the output resistance. So to recall, to calculate the output resistance, you zero the input and you measure the current at the output for a given applied voltage. So let's do that. Let's take the small signal circuit again, ground the input, right? And you want to now apply a voltage at the output and measure the current that's flowing through the circuit. Now if I look at the circuit, I see that there is a resistance RD connected between the output node and ground. And in addition, there is this circuit here. So the resistance is going to be of the format RD parallel whatever is the resistance of this circuit, right? So the output resistance is going to be RD parallel the effective resistance of the circuit. So what we can do is find the effective resistance of the circuit, and then that parallel RD gives you the net resistance at the output. So now let's look at that circuit alone and let's try and identify what the effective resistance of the circuit is. So again, applying KVL at the input, I see that, suppose I call this node, the source node is Vx. I see that my VGS is minus Vx, and that Vx is nothing but I0 into Rs, because I0 is going to divide itself as GMVGS and whatever rest is flowing in R0, and that combines and flows into Rs. And similarly, so therefore the current in R0 is I0 minus GMVGS, or in other words, it's given by I0 into 1 plus GMRS. And now let's apply KVL in the output loop. So my V0 is given by the voltage drop across R0 plus the voltage drop across RS. And so I can write this as I0 into 1 plus GMRS into R0 plus I0 into RS. Or in other words, my output resistance or my resistance of this equivalent resistance of this circuit becomes RO plus GMRS RO plus RS. Now this is an important term to keep in mind because this tells you what the effective resistance is of if you're looking at a resistor through a transistor, right? And for most cases, if GMR0 is very high, we approximate this as GMRORS, right? So this is going to be the output resistance of the circuit that you're looking at without RD. And so the effective output resistance is going to be RO1 parallel RD, on which case it is going to be RD parallel RO plus RS plus GMRORS. So for example, let's find what the output resistance of this stack is. So what I meant to say here is, let's assume that M2 wasn't there. If M2 wasn't there, then the output resistance would have been just RO1, right? The output resistance of M1 would have been just RO1. Now what I'm trying to do is, now I've added two transistors in series. So now if I'm looking at the output resistance from the top node, I'm essentially going to see an impact due to RO1, and I'm looking at this RO1 through M2. So I expect to see a larger resistance, right? So how would you do this? So at node 1, if I look down into M1, I'm going to see RO1, right? And now I'm looking at this RO1 through M2. And so we can say that the total output resistance is going to be GM2 into RO2 into whatever is connected the source of M2, which is R1. So very quickly I can write the output resistance of the stack as GM2 RO2, that is the gain of the M2 transistor times R1. If I want to be accurate, then I can write R out as R1 plus RO2 plus GM2 RO2 R1. And again, in most cases, RO2 RO1 is going to be a large number, and so therefore this is going to be approximately equal to what you get here. So with that, we come to the end of the common source. In the next video, we look at the common gate and the common drain amplifiers.